also maybe 0, 1. And outputs maybe 0, 1, but it depends on the inputs. So actual logic gates can be constructed by using, so actually we have two choices. So first, we can just use simple switches. Here you can see here some relays, some vacuum tubes, transistors and diodes, but it will be too complex and will take a lot of time. And it's old-fashioned. We will not do it, but we will use integrated circuits that actually, contain these logic gates. So the task performed by logic gate is called its logic function. So you should understand difference between logic gate and logic function. Logic gate is some physical things. It's integrated circuit itself that contains this logic gate. But functions is just some operations that these logic gates perform. So logic function can be implemented by, so of course it can be implemented by hardware logic gates. And we will concentrate mostly on the simple, integrated circuits that contain logic gates. But also, we can, do it by programming devices such as microcontrollers or computers. Unfortunately, for now, we don't have opportunity to use microcontrollers. First of all, because we have only 10 weeks, it will be very difficult to include, programming microcontrollers, but I guess you should have some other course, embedded system, when you actually should use microcontrollers, and I hope you will, then after this course you will learn and study embedded systems. But also you can do it by computers, for example, by using some programming language, Python, C++. Actually you can, perform some logic functions. So first we will start with the AND gate. So what is it, the AND gate? So the AND gate is sometimes called the all or nothing gate. Всё или ничего, or all nothing. So let's consider some simple circuit that performs this. Actually, it is the AND gate, very simple AND gate. So it consists of, you could see that it consists of a battery, some lamp, and two switches. So these two switches is connected in series. So if they're both open, we don't have any, so this lamp will not light. If one of them is closed, other is open, it also will not light. So it will light only in those cases when these two, both switches simultaneously will be closed. In this case, we'll have light. So in simple words, the AND gate circuit says yes, light on, at the output only when we have yes at both inputs. So I think it's clear and very understandable. So, but you should memorize this symbol in circuit. We will assemble in multi-slim, and you can see some, for example, in some manual, if you will work with some real circuits, and it has some symbol, and AND gate logic symbol has this symbol. So you should memorize. So this symbol represents AND gate. So simple AND gate has only two input and one output. So let's consider some simple circuit. So here we have AND gate. So it is wired. Its output wired with some LED. So, and here we apply signals to A and B input. Okay, so for each gate we will have truth table, and you should actually not memorize, but you should, understand, and you should feel this truth table. So let's start. So we have input, it's A and B to the gate, and we have output, it's Y, right? So inputs A and B, and the output is Y. So our inputs, it will be, we can say it's just some voltage, high and low, or we can say this binary 0 or 1. It's the same with the B. So what can be our output? Our output is light, lighting or not, or binary 1 or 0. So let's start. When A 0 and B also 0, it means that LID will not light, right? So binary output will be binary 1. So when A 1 and B 0, what do you think? It will light or not?
Not.
Not.
No.
It will. Okay. So next ones, when A 0 and B 1 is similar to the previous, right? So it will not light. And last opportunity, last possibility that we have is just when both of the inputs is high, 0 or 1. In this case, output will be 1 and LID will light. So here you can see some only last line has output with 1 in the case when we have both inputs 1, 1. Okay, so you should actually able to understand what is a truth table, and you should, you know, for example, for such simple logic gates, you should actually, you know, fill this kind of tables. Okay, so next, okay, we'll talk about later. So, but you should. I have you studied discrete mathematics. You're familiar with Boolean expression, Boolean algebra, right? Do you know Boolean algebra?
Yes.
Okay, so it's great. So
You mean
I will
truth tables?
mention what?
You mentioned about truth table or not?
I mean, you should know what is a Boolean mathematics, Boolean expressions, right? Because I guess you've studied discrete mathematics in the first term, I don't know, but I think you're already. Okay, so it is a symbol of the AND gate, and you can just, you know, say input A is ANDed with input B to get output Y. So, but we draw it only in the circuit. But for example, when we'll do some code, or we can just use Boolean expression. So A, and to show that it is ANDed, we use this dot. It is not multiplication, it's just symbol that represent AND function. So A and B is equal Y. So it is from Boolean algebra. Okay, but there is some alternative way. So for example, when we'll do some programming, it's not convenient always use this dot. So sometimes we just, you know, put it together, A, B, but you should understand that it is the same meaning. A and B is equal Y. Okay, so let's make some summary about the AND gate, but before, understand the difference between the terminology. The logic functions just implies a logical relationship between inputs and output, while logic gates suggest a physical implementation. Okay, so actually logic gates perform logic functions. Okay, so here's a table that you should understand, and maybe you will then, when we'll do homework, write down on your notes. So actually we have some possibility to say that we can just say input A is ANDed with input B to get output Y, or we can just, you know, write Boolean expression, or we just draw the symbol, or we can show in the truth table. All of this the same representation of logic function. Okay, so actually we've done with simple AND gate, and next what you should know that the unique output of the AND function is high output only when all inputs are high. So it doesn't matter how much inputs we have. For AND gate, unique output will be 1 only when all of the inputs will be high. So it is you know, some feature of the AND gate. Next one, we will study the OR gate. So it's also very simple logic gate. So in some simple words, we can say that we call that any or all gate, да? То есть или либо все. So here's a simple circuit that perform this logic OR function. So, but in comparison with the previous AND gate, here we have two switches that connected in parallel. So in this case, it's enough if for example, if A switch will be closed, the lamp will light. So for example, if A is opened and B is closed, it also will light. If both is closed, of course it will light. So only it will not light in the case when both these switches are opened. Okay, so let's fill up the truth table. I think it will be very simple. When A open and B open, output will be 0. So when A, for example, closed,
one of them is closed, output will light, yes?
So what second case, let's consider one, A is closed and B is open, so it will be light. Because you can see that current will go through the A.
Yes, yes.
Okay, so right. So here, third possibility, when A is open and B is closed, of course it's similar to the previous one, it will be yes.
Yes, it will be light.
Yes. Yeah, and then last one, when both is closed, you can see that it will light. So actually here we have some unique output 0 only when both of the switches are open. Okay, so sometimes we say it is inclusive OR function because we'll have other type of OR function. We will talk about it later. Okay, I think so for now it's very simple, not so difficult. So here is the symbol of logic gate. So logic gate has this kind of symbol that we represent in circuit. You should also memorize AND OR gate. So please draw it, memorize that OR gate has this kind of this symbol. Okay, so we can say just input A and B are being ORed to produce an output Y. Okay, so but also we can write a Boolean expression. So here you can see some plus symbol, but it's not plus, it's just OR symbol in Boolean algebra. So you can use symbolic, this representation or this. Next, I think it's clear. So let's do some summary with the AND gate. I think this also, so it's Boolean expression, symbol, and truth table. Okay. So next, what you should understand that unique output of the OR function is low output only when all inputs are low. So it doesn't matter how much input we have to the OR gate. So we have on the output 0 only those cases when all inputs will be 0. Other ways we have outputs 1. Okay, next we will talk about one of the simple logic gate. We call it the inverter or just NOT circuit. So actually in the last lab you used this inverter. So it's just it just invert. For example, we have on the input 1, on the output will have 0. If input will have 0, on the output will have 1. So it's very simple, and it is a symbol. You already seen it and actually used in the lab works. So, but it is Boolean expression. So you can see that we need to draw over bar that shows that not symbol. So A, here we have A with bars above. Okay, but there is other way. We will also see how can we write. So let's talk about the inverter truth table. It's very simple. So actually we have one input and one output. So when low, we have output high. When input high, output low. That's it. So it's some alternative representation. Actually, we use in the coding because it's when we do some coding, programming, it's very difficult to put this bar. So it's simple, just use this apostrophe. So it is the same meaning. Okay, next one. So let's talk about a little bit about terminology. So actually, when a signal passes through the inverter, it can be said that the output is inverted or complemented. But also we can say it is negated. So this all the words inverted, complemented, negated, it's the same meaning. Okay, let's consider some interesting circuit when we have, in series, we have two inverter, two NAND circuits. So you can see, so when we apply logic 1, from the first one we get logic 0, but it goes as an input to the second inverter, and it will give us logic 1. So it means that when our signal goes, through the two inverters, we get the same signal. But there is other representation. So actually in previous one, you can see that this bubble, here, but you can see it may be here. So it actually is the same. But this bubble indicates that we need apply low voltage, low state in order to activate some circuit. So just for convenience. But this and this, it's the same. Okay, the similar symbol to the inverter, it's we call buffer or driver. So actually, it is not logic gate because it does not perform any function, but we will use in multislim. But it is not necessary use in multislim because multislim it's a simulation. But when we'll assemble some real, circuit, we need use buffer driver because integrated circuit they're limited in the current. But sometimes we need to, wire our some digital system to some, for example, to some motor or to some LED that needs more current. In this case, we use this driver. This driver just, takes signal and just increase the current of the signal, just power. It's just, the device that give us power. That's it. But sometimes, it's needed that it should invert the signal. There is some buffer that can do it. But we will not, use this kind of thing just for information. But there is some other buffer with, here you can see this buffer has only one input that has two inputs, A and C. So the C input is just control input. So actually, if when you will study computer architecture, you will study some bus, and they use this kind of buffer because by this control input, what's happening here can be, regulated. So here you can see some. It's not truth table, but it is a table. For example, when L low, C. When the input to the C is low and to the A is low, it means that output will be low. When the C is low and A is high, output is high. But when we give to the control input, we give high, it doesn't matter what will be on the A, 1 or 0, because here we have, high resistance. It means that as if this output is, just open to some other circuit that will be here. So it will not affect the work of the circuit that it's wired. For this reason, sometimes, not sometimes, very often in computers, especially buffers are used. Okay, so next interesting gate, we call it the NAND gate. So what is it? It just means NAND AND. So for now we learned AND or NAND gates, which are the three basic circuits that make up all the digital circuits. So for example, consider what kind of gate this one?
And
AND. For example, it is an AND, and then I wire it with the this kind of, what kind of this one?
not.
Not. So actually we get new function because here we have A and B. For example, it will be 1, 1. Here we'll have 1, but after inverters we will have 0. So actually this this combined circuit, we will call it NAND logic, NAND gate logic symbol, or just NAND gate logic. So this invert bubble here you can see, it means that we should invert the signals that AND give us. Okay, so let's so in the Boolean expression you should write A and B, and you can see this long overbar, so you need to write down this long overbar. So this actually means the same thing. So it is NAND gate logic, and it is Boolean expression. Okay, so but let's consider truth table. So inputs and outputs. So for comparison, let's put also AND gates. So for example, A 0 and B 0. What will be AND? What AND will give us 0, but NAND, it is inverted AND, it will give us 1. So for example, when A 1 and B 0, AND will give us 0, but NAND will give us 1. So when A 0, B 1, and AND 0, and NAND will give us 1. So when both inputs are high, AND will give us high, and NAND will give us 0. Okay, so you also should memorize this NAND gate logic symbol. You should understand the Boolean expression, but you should understand that we can actually assemble NAND gate by combining AND and NOT gates. Okay, so here's some summary. So you should know, I've already mentioned Boolean expression. It is some alternative way. You should know the symbol, and you should know the truth table. Okay, also you should know the unique output of the NAND function is low output only when all inputs are high. So actually here we can see. Okay. Next it's NOR gate, yeah? And I think it's understandable. It is the OR with inverter. So NOR gate is actually not OR gate. The output of OR gate is inverted to form a NOR gate. So what kind of circuit is this? What's gate?
OR.
OR. So we wire it with a NOT, and we get NOR gate. So it has its own symbol. It's similar with the OR gate, but here you can see bubble. This bubble means that it inverts the output of the OR. Okay, but it is a Boolean expression. So it is a standard when we draw overbar, but also it's some alternative one. You put on the parentheses and use apostrophe. Okay, so let's see on the truth table. For comparison, we will have also OR. So when A is 0 and B is 0, OR of course 0, but NOR will be 1. When A is 1, B is 0, OR will be 1, and NOR will be 0 because it's you can see it is inverted. Next, A 1, B 0. What will be OR output? What will be
1 0 1.
0 and NOR will be 1, OR will be 1 and NOR will be 0. So here 1 and 0. So it is our truth table for the simple 2-input NOR gate. So here's some summary. So in the English, you just say input A is NORed with the input B yielding output Y. So it is a two version of Boolean expression. It's symbol and truth table. Okay, and you should know the output unique output from the NOR gate is high only when all inputs are low. Okay, but next one it's a little bit tricky, you know, but you should just understand and it will be easy to work with. We call it the exclusive OR gate, or in shortened version we just XOR gate. So what is exclusive? So exclusive OR gate is sometimes referred to as the odd but not even gate. How do you understand odd? What does it mean odd? In Russian.
Так, in Kazakh.
Even.
Нечетный.
Нечетный, yes. Нечетный. How in Kazakh it will be нечетный?
Так.
Так. Окей, Рахмет. Так. So let's but we will not say exclusive OR gate, it will be too long. No? We will shorten and just XOR gate, okay? XOR gate. So it's a symbol. You can see it's similar to the OR gate, but here we have some, you know, curve additional that will indicate that is a XOR gate. So it is a Boolean expression. So actually we have this plus that represent OR, but it is circled. So please, this thing you should memorize, the symbol of XOR gate and its Boolean expression. Okay, so let's look at the truth table. So now maybe for the simple one it will not be clear, but in the later slide next slide we will see more complex 3-input XOR gate. So let's just fill this one. So A 0, B 0, or you know it's 0, but XOR also will be 0 because we need only look at the high input. Okay, A is 1 and B 0. So you can see that number of inputs, we have only 2 inputs, right, guys?
Yes.
And only
Yes.
one input is high. So one input is high. It means number of inputs that high is odd. It means that for OR we'll have 1, and for XOR we also will have 1. So next one, A is 0 and B is 1. So for the OR we'll have 1, but for the XOR also the number of inputs that is high is 1. 1 is odd number. So for this reason also will be 1. So next one, this is very interesting. So A is 1, B is 1, OR will be 1. What do you think will be XOR output?
0.
Why? You're right, it will be 0, but why? Because we have only 2 input is high, but 2 it means even number, right? For this reason it will be 0. Okay, let's read it again and let's consider to the more complex XOR gate. So unique characteristic of the XOR gate is that it produces a high output only when odd number of high inputs are present. So let's consider this 3-input XOR gate. So it has 3 inputs and of course 1 output. So it is Boolean expression, it's simple. So let's consider how much time we have?
12 minutes.
Okay.
12 minutes.
12 minutes, okay. So let's A, B, C will be 0. So what do you think will be output?
True. 1.
No, we need to
0, 0.
0. You need to just take into consideration only high outputs, not. Okay, so next 0 0 A 1 B C 0.
One.
So what 1? Because number of inputs is 3, right? But the number of inputs with the high value is only 1, but 1 it's odd number, right? So 1. So I think the same. We have 1. This is same. We have 1. So next one. What do you think?
0.
0.
Yes, 0. Why? Because 2 inputs will have high value. Only 2 inputs, but 2 is the even number. For this reason, it will be 0. So this one, what do you think?
0.
0. This.
Also 0.
And last one, when all 3 inputs is high, what will be the output?
1.
1.
1, because 3 inputs, 3 number, it's
Odd.
what? Yes. So okay, so what it is the truth gate for the exclusive OR gate with the 3 inputs. Okay, this is just some short summary. So in English, we could say inputs A, B, and C are XORed, yielding output Y. So it is a Boolean expression you should memorize, and this symbol also you should memorize. But of course, you do not need to memorize the truth table, but you should understand how to, fill up this truth table. So also you need to know the unique output of the XOR gate is high only when an odd number of inputs are high. Okay, so next we will talk about the exclusive NOR gate, not OR, NOR gate. So we call it XNOR gate, XNOR. So the term exclusive NOR gate is often shortened to XNOR gate. Okay, I think it's clear. And it is a symbol. So what is the difference between NOR and XNOR gate symbols? What's the difference?
It's
What do you
left
see?
there is additional.
It has this bubble, right? So XNOR gate, NOR gate does not have this bubble, but XNOR gate has this bubble.
Teacher, NOR gate have, isn't it? Like it's not NOR. It's not OR. NOR. It should have.
So exclusive NOR gate. So previously we talked about OR gate. So XOR. So here you can see we don't have bubble.
I just felt like you said about XNOR and NOR. What is this?
Sorry. I mean exclusive NOR gate and exclusive NOR gate. Okay. I'm confused. XOR gate. Okay, XOR gate and XNOR gate. So right. Thank you for this remark. So here it's a symbol, and next is Boolean expression. Okay, so we just add here this over bar. That's it. And next one, truth table for XOR and XNOR. So let's fill out and understand how it's working. Actually, it's similar to the XOR gate, XOR, but the output should be inverted, right? So BA, and for the comparison also I've put here XOR gate. So let's consider A0, 0, what XOR?
0.
0, and XNOR also 0 because it will be 1 because it will invert the output, okay? And next one, 1, 0, XOR will be
0.
No, XOR we already talked, it's 1. But then we should invert to opposite, so XNOR will be 0. Okay? So next, 0, 1, XOR will be
1, 0.
1.
1, and the XNOR we should invert, will be 0. So 1, 1, what will be XOR?
0, 1.
0, 1, so okay. So here, okay, we'll talk about in the Next, the unique output of the XNOR gate is low only when odd number of inputs are high. So let's consider more complicated XNOR gate, 3-input XNOR gate symbol. Okay, so inputs, output. So A, B, C, we have 3 inputs, 0, 0, 0. It's clear, XOR 0 and XNOR 1. Here, what will be?
1, 0.
Here it will be the same. The same. Here,
0,
0,
1.
1.
0, 1. Here,
0, 1.
0, 1. And I think we have also additional 2 possibilities here.
Same.
0, 1.
Same. And last one?
1, 0.
1, 0.
1, 0. Okay, so great. So here, what you should understand, the unique output of the XNOR gate is a low only when an odd number of inputs are high, which is opposite from the XOR gate. So I think it's a little bit confusing, XNOR, XOR, but I think you should understand what is a XOR gate. Then just inverting its output, you will know what is a XNOR gate. So here's just some. In English, you can say inputs A, B, C are XNORed, yielding output Y. So it's a Boolean expression, this logical symbols, and truth table. So for this 3 inputs, it's a little more complicated ones. So okay, still have some time. So let's talk about, maybe you have some questions about the previous slides. No? Is it clear? Okay, let's consider NAND gates, and then we'll over the first part, our first lecture, and after break we'll continue. So sorry for this typo. Actually, it is not nano, it's NAND. The NAND gate as a universal gate. I've already mentioned that at the beginning of this lecture that we can use NAND gate and just come up with AND, OR, NOR, XOR, or XNOR gates. So even just we can create inverter by the NAND gate. So for this reason we call this NAND gate universal gate. And if you will just search some integrated circuits, you will find out that NAND gate is more popular than other ones, because from NAND gate you can assemble other logical gates. So let's consider some how can we create, how can we assemble from the NAND gate other gates. For example, it is inverter, and you should know it's symbol, right? So but you can create inverter from the NAND gate. So actually what you need to do, you just need to connect its 2 inputs together, and you will have actually you have NAND gates, but it will function as will be as inverter. So here you can see AND, it's symbol, but you can wire in this way the NAND gate, and these 2 NAND gate will function as the AND gate. So here it is a OR gate. So by combining, it's more complicated than previous ones, but by combining this way, you can get from the 3 NAND gates, you can get OR gate. So for example, here's a NOR, XOR, XNOR. So just very carefully when you will read chapter 3, just look, ponder about it, think, and just try to understand why this combination creates this one. It's not so difficult to understand. You can just actually tomorrow on the LabWorks we will do some simulation, some assemble some circuit, and partially you will understand. But you need to also think deeply yourself when you will read chapter 3. But it's not too difficult. Okay, I think for now we can now finish the first. And I think I need to. Okay, but before I need to finish, right? And we need to we have other links. So please, guys, so leave this meeting and join to the next meetings. Okay.
Okay.
Okay. See you in 20 minutes. Do you have some questions to me? You can ask.